Homework 3.4, the rational zero theorem, video 1. Homework due Wednesday, May 27th, 2020 at 11:59 p.m. Before we jump into this series of videos, I just want to make a quick comment about the homework problems you should be trying. You'll notice on some of the videos I won't put anything here because we will be developing theorems and techniques. And not necessarily working a specific example, despite how this one may look already. But when I do write try homework problems, I'm going to use the same notation I did in the previous series, where I will write problems that are directly like these. I'll write the numbers here, but problems that involve this but aren't entirely this will be in parentheses. And I keep looking at my list over there, which is off the screen, but there's one type of problem that we will see around video 3. Well, we're going to build up to it. That will be in almost every single problem in the homework. So don't be surprised when this suddenly goes from nothing to almost everything. Okay, so to kind of pick up where we left off at the end of the video, the last video for homework 3.3 and video 7, we had found the zeros of this function, f of x equals x to the third power plus 2x to the second power minus 5x minus 6. And the zeros were 2, -3, and -1. And remember what that means. A zero of a function is a number that makes the function equal to 0. So by saying that 2, -3, and -1 are zeros of f of x, all we're saying is f of 2 equals 0, f of -3 equals 0, and f of -1 equals 0. And you may recall, and if not, you may want to watch the previous video, that when this question was posed to find the zeros of that function, you were given a hint. The hint was, this is one of the zeros. As a consequence of that and of the factor theorem, we got to set up a synthetic division problem, which allowed us to find the factor associated with this zero and another factor which went on to find these zeros. But at the end of the video, I posed a question. The question was, if we were not given one of the zeros to set off the synthetic division problem, how do we begin? And the bigger question was, where are these zeros located in the original function? Because if we're going to do a synthetic division problem, we have to have a divisor, or a box number, if you will. So there has to be some hint somewhere as to what to try for that box number. So what I'd like to do in this video is kind of figure out where these numbers are embedded. Now you might be thinking, okay, there's a 1 here and there's a -1 there, maybe that's something, and there's a 2 here and there's a 2 there, maybe that's something, and it's not a bad idea to speculate, but I want to see if we can literally recover where these numbers came from back in the original function. Now, how are we going to do that? Well, we're going to take advantage of the factor theorem. The factor theorem said the following are equivalent, but I'm not going to list all of them. I'm just going to list something that we can take advantage of. If f of c equals 0, then x minus c is a factor of f of x. The third part of the equivalency was f of x divided by x minus c has a remainder of 0. We can use this to our advantage. The forward flow of this problem was get that factor, set each factor equal to 0 and solve. But if we want to reverse the process, we start with the solutions and turn them back into factors. So for example, if x equals 2 is a 0, which it is, we're told that, and you can verify it if you don't believe me. This means that x minus that is a factor. And if x equals -3 is a 0, in fact, let me list zeros factors. If x equals negative 3 is a 0, then according to the factor theorem, x minus negative 3 is a factor. Wait, I really shouldn't leave it like that. Anytime you have minus and negative, you should almost always just turn it into a plus. And the other 0 is negative 1. And so what would its factor be? In short, x minus negative 1, and even shorter than that, x plus 1. So zeros can go back to being factors, just like factors can turn into zeros by setting them equal to 0 and solving. Well, we're going to FOIL all this out, but as we do, I want you to try to focus on where these numbers go, because we're trying to figure out where they are in the original problem. So if we're going to FOIL 3 sets of parentheses, we just need to do them 2 at a time. So let's multiply all this out. Starting with the first 2. I'll go ahead and FOIL it and combine like terms. You'll get x squared plus 3x and minus 2x is plus x, and then negative 2 times positive 3 is negative 6. We haven't messed with the 1 over here yet, but where's the negative 2 and the 3? Where can they be recovered from here? There's actually 2 places. If you add them, you get 1, and if you multiply them, you get negative 6. So which one should we focus on? Well, how many addition problems do you know that equal 1 using only integers? There's an infinite number of them. You give me any number, I can find something to add to it to give 1. 15, all right, and negative 14. Negative 20 and positive 21. So I can find an infinite pair of integers that have a sum of 1. But how many pairs of integers have a product of negative 6? And notice I said integers. Well, there's 1 and negative 6, negative 1 and 6, 2 and negative 3, negative 2 and 3, and those are the only pairs of integers whose product is a negative 6. So in terms of keeping track of where the negative 2 and the 3 go, I think it's a better idea to keep track of the product, because there's a limited number of ways to have a product of integers that equals negative 6, as opposed to a sum of integers that equals positive 1. All right, well, let's keep going. If I multiply all this out, and it would require a lot of distributing and combining like terms. In fact, let's go ahead and do that. Let's distribute the x squared. We would get x cubed plus x squared. Let's distribute the x. We would get plus x squared and plus x. And let's distribute the negative 6 to get negative 6 minus 6. Now, where was this negative 6 used? In these 2. And where was the 1 used? It was actually used in this one, and this one. If you check where all the distributions went. So the negative 6 and the 1 were used many, many, many places, but guess which one place used both of them? Here. So we're going to focus on the fact that this negative 6 and that negative 1 landed here. And the rest of the stuff gets put together. It better match that. X cubed plus 2x squared minus 5x minus 6. And look at that, we got back to the original function. But remember, what we were trying to do here was keep track of where the original zeros went. Not necessarily their signs, because the signs can change depending upon what you do, but their values. So just to retrace our steps, the 2, the negative 3, and the negative 1 appeared as these constant terms in the factors, and as we multiplied, all 3 of them eventually got multiplied together to make the constant term in the polynomial. So the answer to where were the zeros embedded was here. Now be careful. That doesn't mean that it was going to be negative 1, negative 3, and 2. Why wasn't it positive 1, negative 3, and negative 2? Or why wasn't it 1, negative 1, and 6, or some combination? So saying that the zeros were embedded in this constant term doesn't mean you can just look at it and say, I know what the zeros are. But remember, if I don't give you a hint for the box number, you have to make an educated guess, and it's this constant that's going to help us make that educated guess. Now there's a little more to the story that I haven't told you yet. So I'm going to set up another example where we already have the zeros and see if we can discover where all of it is embedded, because I haven't shown you the whole story yet.